again. Okay, so we start the discussion on dot product. Now we have some physical motivation for defining a dot product. Now I'm not saying that the dot product is defined only because of this reason, but we actually in physics we have a lot of situation that requires the use of the dot product. So we define the dot product like this, and the physical motivation that is the work done that we want to discuss now is only one of the motivation. So how to define work done? If I apply a force F on the body and the displacement of the body is in another direction, then what would be the work done by the force? The work done by the force is not simply F times S, right? Because F and S are vector, and now F is not in the direction of S. it makes an angle theta with S. So the first thing is that I have to resolve the component of the force F in the direction of S. So I find the component F parallel. F parallel means I resolve the force component of the force in the direction of the displacement, parallel to the displacement. So the work done can be defined by that component of force, that parallel component of force multiplied by the displacement. So in terms of this angle phi, I have F cosine theta multiplied by S, or Fs cosine theta. And in physics, it is conveniently defined. This combination is defined as the dot product between the vector F and S. Now notice that there is a dot between the two vectors. It means the two vectors multiply together using the definition of the dot product. Okay, and that will result in a scalar. You notice that Fs cosine theta, this combination is a product of three scalars. So it's of course a scalar. Okay, it is a product of the magnitude of F and S together with the cosine, the angle between that. So that must be a scalar. So the result of the dot product between two vectors will give you a scalar. So that's how we define the dot product. A dot B is AB cosine theta. So you can imagine now the dot product can be, you can have an appreciation of some special case. When theta is zero, that means the two vectors are parallel. In that case, A dot B is simply AB. Now you can see when theta is zero, cosine theta is just one. So A dot B is just AB, okay? And when theta is 90 degrees, then cosine theta is zero, right? And so the two vectors are perpendicular to each other, and the dot product will be zero, okay? So two parallel vectors will use a dot product equal to the product of the magnitude, and two vectors perpendicular to each other will use a zero dot product, okay? And you can also think of the dot product as the projection as a component of one vector in the direction of the other, multiplied by the magnitude of the other vector. Okay, in this case, I project B along the direction of A. I get B parallel equal to B cosine theta. And when I use B cosine theta and multiply by the length of A, I got the dot product. Okay, you can think of the dot product this way. Now the dot product has certain properties. The first thing is that it has a symmetry between A and B. A dot B is equal to B dot A, and it's obvious because both A dot B and B dot A, they yield the same result of AB cosine theta. And the dot product also have linearity. It means that if I have a vector A added to vector B, I add the two vectors first to get the resultant, and then I form a dot product of that resultant with a vector, another vector B. Then the dot product can be distributed on each of the vectors inside the bracket. That means I can form a dot product of B with A1 first, form a dot product of B with A2, then I add up the two dot product. Okay, so the B vector can be distributed just like simple algebraic manipulation to each of the term inside the bracket. Now, you may say, well, this is trivial. Why you would like to say that? This is not trivial at all. I would say. Now, you notice that this is no similar to an ordinary algebra. In ordinary algebra, you simply have the multiplication and addition and subtraction. But now we are talking about the dot product. It's different. You see, on the right-hand side, it is about the sum of two scalar. The plus sign here is a sum of two scalar. I form the dot product first, respectively with A1 and A2. I got two numbers, and I add up those two numbers. So that is about the addition of two scalar on the right-hand side. But how about on the left-hand side? The left-hand side means inside the bracket, I'm adding up two vectors. I am using the tip to tail method to add up the two vectors. And then I form a dot product of the resultant with the vector B. So even the plus sign, they mean differently on the two sides of the equation. They are not meaning the same thing. On the right side, they mean the addition, the simple addition of two numbers. But on the left-hand side, it means the addition of two vectors. So the equality is not trivial. It may not hold. We have to prove it. Okay. And the last property that is important in physics is that it's independent of coordinate. We'll talk about it later. Okay. Now, we just give you a geometrical proof. It is not rigorous, but I just want you to see what it means by A1 plus A2 dot B equal to A1 dot B plus A2 dot B. Now, A1 is here, the blue arrow. A2 is here, another blue arrow. The resultant, A1 plus A2, is a red arrow. Okay. Now, what the left-hand side means is that I have A1 added to A2 first, which gives me the red arrow C. Okay. And I form a dot product with this red arrow C with the vector B, which is in this direction, I suppose. Okay. And so, so I resolve the vector C in the direction of B. So I got C parallel here. C parallel is the component of C in the direction of B. Okay, so this is C parallel. I project the vector C along the direction of B. So this is C parallel. So I got the left-hand side as C parallel multiplied by B. Now I work on the right-hand side. The right-hand side consists of A1 dot B and A2 dot B plus added together. So A1 dot B is the projection of A1 in the direction of B, the component of A1 in the direction of B. So I got A1 parallel multiplied by B. For the second vector, I got, after projection to the B direction, I got A2 parallel multiplied by B. Now, there are two numbers, right? So I can easily extract a vector of B out. And inside the bracket, I have A1 parallel added to A2 parallel. But you can see from this figure, A1 parallel plus A2 parallel is just equal to C parallel. Okay, so now I have C parallel B. Okay, and that makes my right-hand side equal to the left-hand side. And so for this situation, I prove the statement. Okay, I've proved the linearity properties of the dot product. Now, we actually define the dot product in this way to preserve the property of linearity. Okay, if the dot product is not defined this way, it's not defined as a projection, you will find that the properties of linearity will not hold. Now, let's examine this. Some people say, why don't we define the dot product just by the magnitude, the product of the magnitude? Suppose we define the dot product A dot B by the product of the magnitude of the two vectors, but without the cosine factor. Why can't we do that? You can do that, but if you do that, then you will run into difficulty when using algebraic manipulation. Why? Because linearity will not be preserved. Let's consider now I have two vectors A and B. First, I consider A added to minus A, then I dot with B. Okay. Now, If this is the case, then A minus base must be 0, right? Then I have 0 dot with B, then I got 0 result, according to this definition, right? However, if I distribute the vector B onto each of this vector, I have A dot B plus minus A dot B. But since you are defining the dot product without the cosine, both A dot B and minus A dot B, they give you the same AB, okay? Because you are defining the dot product now without the cosine vector. So the minus A dot with B still give you AB because you are defining it with the product of the magnitude only. So I got 2AB, right? And so what? And so the linearity property will not hold if you define the dot product like this. And so that would not be very useful in physics. Because even linearity will not hold, then you will find it very difficult to manipulate this dot product in a calculation. Okay, so that's why we don't define it like this. We define it using the product of the magnitude and also with the cosine factor. Now, with linearity, we can actually do a lot of things. Suppose we have two vectors expressed in terms of the basis vector, AXI, AYJ, BXI, BYJ. These are the vector A and B. Now, let's form the dot product between A and B. If we express them in terms of the basis vector, and if we apply the property of linearity, that means I can distribute the dot product of B with each of the component like this. Okay, I have an AXI dot with B, then I have AYJ dot with B. And again, I can apply linearity again. I can distribute this AXI to each of these two terms, and AYJ to again to each of these two terms. So I got 4 terms eventually. The first term is AXBX I dot I, the second term is AXBY I dot J, the third term is AYBX J dot I, so last term is AYBY J dot J. And of course, I dot I and J dot J, they are both equal to 1. Because they are parallel, and so the cosine factor is 1, and the magnitude of the vector are both 1, so got the result of 1. I dot J and J dot I are 0 because the two vectors are perpendicular. So we don't have the I dot J and J dot I term, and I dot I and J dot I just give me 1, and so I have AX BX plus AY BY. Okay. Now, the important thing is that I have successfully expressed the dot product in terms of the component. It is easy to find the dot product from the component. I just multiply the component, X component together, and the Y component, I multiply them together, and then I form a sum between the two, and I find the dot product. It can be easily generalized to 3 dimensions. If I have the Z component, I also multiply the Z component of the two vectors together. I add to the product of the Y component and X component, I got the A dot B. Okay, so in this step, linearity hinge. It hinges on linearity. If I don't have the property of linearity, I cannot distribute the dot product to each of the terms in the bracket to prove this result. Okay, so that's why linearity is important. Now, you can do it at home. I think this is a simple exercise of a dot product between two vectors. Okay, and you can also find the vector between the two vectors. Okay, now I do it quickly with you since I don't have enough time. I prefer to do it together with you now. Now, so this is A dot B. What is A dot B? I have the X component of the vector A multiplied by the X component of the vector B. So I now have 3 times 2, right? And then I have the Y component of A multiplied by the Y component of B. Okay, the Y component of B, you don't forget the minus sign before the coefficient. Okay, and for the Z component, A doesn't have the Z component, so that is a 0 multiplied by the Z component of B is 2. So now I have 3 times 2 is 6. 4 is 20, minus 20, this is 0. So now I have minus 40 for the dot product. But again, I know A dot B is equal to AB cosine theta, where theta is the angle between the two vectors. And now I'm required to find that angle. And so I can express the angle cosine theta as A dot B divided by the magnitude of A multiplied by the magnitude of B. How to find the magnitude of A and magnitude of B? Well, by Pythagoras theorem. A is equal to what? AX squared plus AY squared, square root. And that is, of course, 5, right? And how about B? B is square root of 2 squared plus minus 5 squared plus 2 squared. And this is 4 plus 25 plus 4, right? And we have 33 square root. And so this will be equal to what? This will be equal to minus 14, which is A dot B, divided by 5 square root 33. Okay, so you use a calculator, you take the arc cosine, and you will get an angle larger than 90 degrees because it's in the second quadrant. Okay, so that is the idea. Okay. Now, the important properties about the dot product is that it's independent of coordinates. What is the meaning of that? What is the meaning of a dot product independent of coordinates? Now, suppose I have a certain coordinate system I call the axis x and y. And I can express the vector A in terms of the component ax, ay, bx, by in that coordinate system, right? And as we have proven that A dot B, which is equal to AB cosine theta, is AX BX plus AY BY. Is that right? But how about if I have another coordinate system that is tilted at an angle to the original coordinate system? Suppose we have a new coordinate system called X prime and Y prime. This new coordinate system is tilted by an angle, by a certain angle, I don't know, relative to the original coordinate system XY. But coordinate is something chosen by us, right? We can choose whatever coordinates we like. It would not affect the physics we learned, right? So in a new coordinate system, I can equally resolve the vector A and B into their components. And I got AX prime, AY prime, BX prime, and BY prime. They are respectively the component of the vector A and B. And I also got the new basis vector, I prime, J prime, the new basis vector in this coordinate. Okay. Now, the dot product is still, the dot product is still equal to AB cosine theta. And if you believe that I can do it in the same way for the new coordinate system, I can form a dot product between A and B using the component. And I should get AX prime, BX prime, plus AY prime, BY prime, right? It should be in the same form as the old coordinate system. The result should be in the same form. Now, but you notice that I know that they are equal, but they doesn't look like to be equal. The XY component that we resolve in the old coordinates are all different from the XY coordinates that we got in the new coordinates because they refer to different coordinate axes. So all this number, AX, AX prime, BX, BX prime, AY, BY, AY prime, BY, BY prime, they're all different. But it turns out that this combination remains invariant with respect to coordinate transformation. Okay, do you understand what I mean? All the numbers are different, but it happens that this combination remains the same, no matter how you rotate the coordinates. It's quite a miracle, right? In order to prove it rigorously, you have to go to learn some matrix transformation, rotational matrix, those kind of thing. I'm not going to talk about those kind of things, but I only highlight that both of this combination should be equal to AB cosine theta that we define for the dot product. So you believe it these two combinations to be the same. Now, in problem application in physics is like this. You have played with inclined plane in your high school, right? Suppose you have a mass that is sliding down along an inclined plane. An inclined plane at an angle theta makes angle theta vertical. Suppose the block now move a displacement s along the inclined plane. The force of gravity is vertically downwards, right? So when I'm asked what is the work done by the force of gravity when the block moves a displacement s along the inclined plane, I can do it in two ways. The first way is that I use a coordinate system with x-axis along the inclined plane and y-axis along perpendicular to the inclined plane. In that case, the weights of the object, the force, can be resolved into two components, right? Since the force is vertical downward, its x component is mg sine theta, right? This is the x component. And the y component, mg cosine theta. But it's in the negative direction, so I add a negative sign. Therefore, the displacement is simple. It's simply s, right, in the x direction. So you see the dot product between f and s will be mg sine theta multiplied by s. The y component doesn't contribute. We only have the x component multiplying together. So it gives you mg s sine theta. But I can also work on the same problem using another coordinates. I can define the x prime coordinates, the x prime axis, to be in the horizontal direction, while the y prime axis to be in the vertical direction. In this case, the force that I'm concerned is the weight. It only consists of one component. That component is the y component. It's minus mg j prime, right? Because it's vertically downwards. Okay. But now the s, the displacement, should now be resolved into two components. The x component is s cosine theta, and the y component is minus s sine theta. But as soon as we form the dot product between the two vectors, you can see only the j components matters. The I component does not contribute. The minus sign cancel, again, it yields mg s sine theta, which is the same as this one. Okay. Now, so that means the dot product is independent of coordinates. Even if you use a tilted coordinates, we calculate all the components of the two vectors. They are different from the original coordinates. We form a dot product and we find the dot product remain the same. That is important because the coordinate is something that we define, and physics cannot be dependent on something we define, right? If you use a tilted coordinate system, that must yield the same value because the work done is the energy transfer, and the energy transfer should not depend on the coordinate you choose. You use whatever coordinate you use to calculate the energy transfer, and you should get the same value. If that represents some real physics, right? So it is important for the dot product to have this property. So so physics written in the language of vector, written in the language of dot product is important because it makes the physics independent of the coordinate you choose. Okay, so physics does not depend on what kind of coordinate you choose. You can just tilt it in whatever way you like. It just gives you the same result in terms of the quantity that correspond to the real world. Now I have two examples for you. The one example is the proof of a cosine law. Okay, the vector AB is there, right? And so A minus B is the vector that goes from the tip of B to the vector to the tip of A, right? Now, so I have this vector equation. I form a dot product of the vector with itself. So on the left-hand side, I form vector dot product of the vector C with itself. So it becomes C dot C. Because the two sides are always equal, so when I form the vector dot product of the vector A minus B with itself, it must be equal to C dot C, right? So I on the two sides, I just form a dot product of the vector with itself, and they remains equal, right? Now C dot C becomes C squared, and by using the linearity property, I have A dot A minus A dot B minus B dot A and plus B dot B, right? And so A dot A become A squared, B dot B become B squared. These two combination, because the dot product has a symmetry between A and B, they become 2A dot B. But what is 2A dot B? A dot B by definition is 2AB multiplied by cosine the angle between them. So the resultant formula is what? Is what you learn in high school, is the cosine law. The opposite side of a triangle C squared equal to A squared plus B squared minus 2AB cosine theta. It's what you learn in high school. Now you are able to do it, to prove it using a few lines with dot product. Okay. In your high school, you may have proved this formula by looking at the complicated angle, the projection, whatever. But now you'll be able to prove it in just a few lines with the dot product. So linearity actually is an important property, because we hide all those projections, all those complicated angle in the dot product. And with linearity, we can manipulate with that. So it saves us a lot of writing. Okay, and linearity also allows you to preserve the property of many geometrical quantities. So you can write it like this. Now another example is that is the compound angle formula. You might learn it in your high school, right? Cosine beta minus alpha is cosine beta cosine alpha plus sine beta sine alpha, right? For those who haven't learned it, no problem. You accept it as a formula, and we should be able to prove this formula in just a few lines of writing. Okay. Now, cosine beta minus alpha is not just cosine beta minus cosine alpha. That's not true. It is a combination of cosine beta, cosine alpha plus sine beta sine alpha. So let's see how to use vector to do that. Suppose now the angle alpha is the vector A, makes the angle that the vector A makes with the x-axis. I call this angle alpha. The angle that the vectors B makes with the x-axis is called beta. Now, so obviously from this figure, I define the angle gamma as beta minus alpha is the angle between the vector A and vector B. So this angle, the angle between the two vectors is defined as gamma, which is beta minus alpha, right? Now, so now I write out the vector in terms of the component. We know that the dot product between the two vectors is AB cosine gamma. That is the definition. But I can also write the dot product in terms of the component AX, BX plus AY, BY, right? But I can write AX, BX, AY, BY in terms of what? In terms of alpha and beta. AX is what? AX is A cosine alpha. Is that right? And BX is B cosine beta, right? AY is A sine alpha. And BY is B sine, sine beta. Is that right? Now, when we compare this with this, after canceling the factor AB, we got this formula, exactly this formula. Can you see that? So I only need 2 lines of writing. to prove this complicated cosine law, this compound formula that I learned in high school. Okay, because the linearity allows me to do so. All the hidden projection, they are hidden in the component, okay, and in the dot product. So I can use it to prove it very easily. Okay, so that is the important things to learn. Now we are able to do a complicated example. Suppose we want to fly between two places on the surface of Earth. We want to ride an airplane to fly from Hong Kong to say New York or to South Africa, okay, to Cape Town, for example. What is the shortest flying distance between these two places? Well, the answer is that this is a big circle. If you draw a big circle joining the two places, that is the shortest flying distance. And the big circle corresponds to a circle joining these two places, and with the center of the circle being coincide with the center of the Earth. That is called a big circle. Okay. So how to find this arc length? That is the problem. Okay. How to find the shortest flying distance? S. But we know, we already have learned how to find the Cartesian coordinate of Hong Kong and New York in terms of the spherical coordinate, right? The spherical coordinate of Hong Kong is just given by the latitude and longitude, right? For Hong Kong, the latitude is 222.5 degrees north. The longitude is 104 degrees east. And for New York, we have 42.7 degrees north and 76 degrees west for the longitude, right? And using this angle, we can convert this angle into the Cartesian coordinate of Hong Kong. So I can express Hong Kong in terms of the Cartesian component X, AY, and AZ. Again, I can do the same thing for New York, right? We actually have done this before, right? Do you remember this? For Hong Kong, we have these three numbers for X, Y, Z component. And so I can do the same for New York, right? And I got BX, BY, BZ. And when I form the dot product between the two vectors, I got, by definition, R squared multiplied by cosine theta, where cosine theta is the angle obtained by this arc length at the center of the Earth. Okay. Now, so, but I can also calculate the dot product by AX, BX plus AY, BY plus AZ, BZ, right? Because I have already do the conversion. So that means when I use a dot product, I divide it by R squared, and then I take arc cosine, I get the angle theta. And if I multiply the angle theta by R, of course, theta is in radian, I will get the shortest flying distance between the two places. Okay. So let's do it in your homework. In homework, you will be given two places on Earth, and you are required to find the shortest flying distance by using a dot product. Okay. Now we are also interested in introducing to you the cross product. Now we also have a physical motivation for that, but of course that is not the only physical motivation. There are a lot of physical motivation. The torque or the moment of force is only one of the physical motivation. Now in your high school study, you learn that a force can have a turning effect, and that turning effect is known as the moment of force. Now we have a more sophisticated term for that, and that term is torque. Torque is nothing but just a moment of force. Now, if you are turning something, like turning a door about the hinge, then you probably would like to apply a force at a certain distance from the hinge. And that distance is described by the vector R. This is the hinge of the turning. And now I apply a force at a position R from that hinge. Okay, so this is the vector R. And I apply a force F in a direction that makes an angle theta with R. R is a radial direction, is a radial outward direction, and my force acts in a direction that makes an angle theta with R. Okay, and so how do I measure the moment or the torque? Well, the moment is measured by what? I first resolve the force into the perpendicular component of pearl that is perpendicular to R. It is this component that causes the torque, right? The parallel component does not cause a torque. So I first resolve the force into the perpendicular component F pearl, and that's given by F sine theta. And I multiply by the distance R to get the moment or the torque. So that combination is R multiplied by F pearl, or if I like, I can express it in terms of the angle is equal to RF sine theta. Okay, so I define the cross product between these two vectors with a magnitude equal to RF sine theta. Okay, and how about the direction? How do I express the direction? Well, I express the direction by the so-called right-hand rule. If this object tends to rotate in this direction, then I use my forefinger of my right hand to curl around like this to represent the direction of the rotation. Okay, so if I turn the door like this, the rotation will be going in this direction. So I use my forefinger, I curl it around like this. And the direction of my torque is defined as the direction of my thumb. Okay, so if the object tends to rotate like this, okay, along my direction of my forefinger of my right hand, then the direction of the torque that produces this rotation will be denoted by the direction of my thumb of my right hand. That is the definition. Okay, that definition allows you to define a rotation in three dimensions. If you are saying that a rotation is in this direction, the torque is in this direction, what you actually means is that the object is trying to rotate this way. Okay, if you are saying that the rotation is in this direction, the vector torque is in this direction, what you are saying that is the torque tends to rotate the object in this direction, with the direction with our forefinger. Okay, is that clear? So that is exactly how we define the cross product. If I have two vectors A and B, then the magnitude of the cross product between A and B is AB sine theta, where theta is the angle between the two vectors, and the direction will be defined by the right-hand rule. I use my forefinger to curl from the direction of A to the direction of B, and the direction of my thumb is the direction of the cross product. So the cross product between two vectors result in another vector. It is not a scalar. Okay, in a dot product we get a scalar, but in the cross product between the two vectors give you a vector, give you another vector, and that vector has a direction defined by the right hand rule. Now, in your high school, you may have learned some in electromagnetism. You may learn the Fleming left-hand rule. Sometimes they call right-hand rule. I don't remember what right-hand or left-hand. You use this kind of right-hand rule to figure out the direction, right? But in university, forget about all those left-hand rule and right-hand rule. We do not use those left-hand rule and right-hand rule anymore. We can express everything that involves the three directions in terms of the cross product. Okay, so the cross product is the only thing you need to remember. The right-hand rule. You use the right hand. You go from A to B with your forefinger, and the cross product is in the direction of your thumb. Okay. When the two vectors are parallel to each other, A cos B is 0 because angle theta is 0. when the two vectors are perpendicular to each other, then A cross B is simply AB, okay? Because sine 90 degree is 1. So A cross B just give you AB. So as I say, physical law involving both the left hand and the right hand, they can always written in terms of the cross product, okay? Now, but the cross product has an asymmetry. It is not like the dot product which has a symmetry. It is asymmetrical or antisymmetrical. A cos B is in the opposite direction to B cos A. Now you can easily see that if I go from the vector A to the vector B, then my thumb will go up in this direction. But if I go from the vector B to the vector A and I use my right hand again, my thumb will go in the downward direction. So that means that's why A cross B and B cross A are in opposite direction. They are the same, but with the opposite sign. Okay. And similarly, we have the linearity for the cross product, but we won't go into this detail. We just want you to realize that the linearity holds, but we are not going to prove it. Okay. And also, it's independent of coordinate. You can also prove it. Okay. And we skip all those mathematical details in order not to obscure you with the complicated mathematics. Now, but how can I express a cross product? Well, not difficult, because I have the basis vector and I have linearity. Okay. Now, the basis vector goes like this. This is I, this is J, this is K. You can easily see that when I cross J, it gives me K. When J cross K, it gives me I. And when K cross I, it gives me J. It's like a circle. It's like a circle. If I start from I, which is X, and I cross with J, that is Y, I got EZ, that is K, right? So again, if I start with J and K, I got X. J cos K is I, okay? So it's easy to remember. I just follow this circle. I cos J is K, J cos K is I, and K cos I is J, okay? So if I go like this in this direction, I always get a plus sign, okay? But when I go in the reverse direction, suppose I have J cos I, if I go from J to I got a minus K. And similarly, if I go from I to I cross K, then I got minus J, okay? So whenever you go in the right direction, you got the positive sign. Whenever you go in the reverse direction, you get a minus sign. And you can easily verify all this sign by using the right hand and the coordinate like this, okay? Now, so we are ready. I better finish it before letting you go, because that will be incomplete. And now I form a dot cross product between the two vectors, and I write them out in terms of the ijk component. Okay, so how many terms are there? If each vector has 3 terms, then they multiply together. The two vectors multiply together will have 9 terms, right? 3 times 3 is 9. But most of the terms, but the 3 of the terms are 0, because I cross I, J cross J, and K cross K, they are 0. Okay, they are parallel. When 2 vectors are parallel each other, the cross product is 0. Okay, and what is left is I use this cycle. I cos J is K, and K cos J cos K is I, and in the reverse direction I have a minus sign. So eventually I got this complicated expression. The I component is AX, AY, BEZ minus AEZ, BY. The J component is AEZ, BX minus AX, BZ, while the K component is AX, BY minus AY, B6, X. And if you are familiar with a determinant, now this looks a bit complicated. But if you are familiar with a determinant, you can express the resultant vector C by this determinant. IJK on the first row, the vector A on the second row, whether it be on the third row. And you expand this determinant, you got this combination. Now, for those who don't know how to use determinant, I can teach you a simple method. That method works only for 3 times 3 determinant. Now, I skipped this slide in the lecture notes. I better upload it again to include this slide. Now, the idea is simple. This is the determinant that we have. Now, I extend the determinant by 2 columns. I just copy the first column and the second column, and I put it here, okay, on the right-hand side of the original determinant. Then I draw the diagonal, okay? For the diagonal that goes downwards, okay? For example, I multiplied by AYB z, it carries a plus sign. So here I have AYB z as a positive, with a positive sign as the I component, okay? And I draw an upward diagonal. And whenever I draw upward diagonal, I assign it with a negative sign. So for the I component here, I have AZBY. But since it's go up, so I add a negative sign. So here I have negative AZBYI. Okay, and so similarly for the J component, here I have AZBX plus sign, and then I have AXBZ with a minus sign. So I got this term. Okay, and also I can do it for the K component. That's how you memorize it. Okay, now let's stop here. I have gone too far.